Okay, so limits at infinity, you learned it before as end behavior. What does the graph look like as we look way to the right and way to the left? Well, we get horizontal asymptotes at the line y equals L if, when the graph goes to positive infinity, we get a finite number that it's approaching, a finite y value. Or when it goes to negative infinity, and they do not have to match. You could have a graph that has two different horizontal asymptotes. Okay, so when we're looking for the horizontal asymptotes, we're looking at what is happening at positive or negative infinity. So we're going to look at the limit as x goes to infinity of this thing. Well, a direct substitution gives me 5 minus 2 over infinity squared. All right, the 5 is just going to be 5, right? But what happens when we have 2 over infinity squared? Well, what's infinity squared? It's still infinity, right? Huge number, even more huge now. So if I have 2 pizzas, and I split those 2 pizzas among the entire population of China, how much pizza does each person get?
Not a whole lot.
None.
I'd be surprised if they got any with how small you have to cut it.
Right? I mean, you wouldn't even be able to see those crumbs. They'd be so tiny. That's none. Okay, when you get a number over infinity, whether it's positive or negative, doesn't matter. Everybody gets no pizza. This goes to 0. So the answer to this problem is 5, because our 2 over infinity squared is going to go to 0. Okay, the next problem, limit as x goes to infinity of 3 over e to the x. I get 3 over e to the infinity. E's a number, it's 2.71 something. If I raise 2 to the infinity, I'm going to get infinity, right? So 2 point whatever it is, raised to the infinity is infinity. We get 3 divided by infinity, 0. So if I was asking you about horizontal asymptotes, you would tell me for the first problem, y equals 5 is the horizontal asymptote going off to the right of that function. And for the second one, you would tell me y equals 0 is a horizontal asymptote when I look at the end behavior going to the right of that function. All right, limit as x goes to infinity of sine x over the square root of x. So if we do a direct substitution here, I've got sine of infinity over the square root of infinity. Well, square root of infinity, that's still infinity, right? But what is sine of infinity? As we go off to infinity, when we look at the sine curve, does it approach a single y value? It just keeps oscillating, right? So we have a number that's between -1 and 1 for sine. It's a finite number divided by infinity. What do we get for this? We get 0. Okay, on the next problem, if I do a direct substitution, I've got 2 times infinity minus 1 over infinity plus 1. Now let's think about this. If I have $10 billion, does that 1 really matter? That 1 is insignificant. So I have 2 times infinity over infinity. Those infinities are the same size infinities, right?
Tell me there's different sizes of infinities.
There are different size infinities.
Oh, gosh.
Okay, we get 2.
Some infinities are greater
Just
than
think of
other
infinity as
infinities.
another variable.
Okay, so in college algebra, this would be one of the ones that you were taught a rule for. And the rule was, if you look at the degree of the numerator, which would be a 1 here, and the denominator, it would be a 1 here, the horizontal asymptote would be the ratio of the coefficients, all right? This would be a 1 there. So it would be at y equals 2, which is what we got. Okay, now rather than think about different size infinities, let's just look at our function first. And then I don't have to think about the different size infinities. When it's an infinite limit, I can say, wait a minute, anything but the highest term, highest degree term, is insignificant. So let's not even look at those negative ones. And if I don't look at those, this appears to be the limit as x approaches infinity of 2x over x, but that simplifies, right? So it would be the limit as x goes to infinity of 2, and we know the limit of a constant is just that constant. Okay, so our next example, there's another rule for it in college algebra if I was finding the horizontal asymptotes. But let's use the method we just employed of getting rid of anything insignificant. So if I have 2x plus 5 in the numerator, and we're talking about an infinite number for that x, that 5 doesn't matter to me. And I have 3x squared in the denominator, that 1 does not matter to me. So this looks like the limit as x goes to infinity of 2x over 3x squared, which simplifies to the limit as x goes to infinity of 2 over 3x. We plug in our infinity, and now we're dividing by infinity, right? So what do we get?
0.
0.
Yes, I was the no horizontal sign. That's what I was
Okay, so when I look at this next function, my 5 is insignificant. My 1 is insignificant. So what does this function actually look like? If I simplify 2x cubed over 3x squared, that's going to look like 2x over 3. And if I plug infinity into that, two times infinity is still infinity, right? So in this instance, we have a limit at infinity that is an infinite limit.
What would that look like?
All right, let's look at this one. The limit as x goes to infinity of 1 over 1 plus e to the negative x. All right, now I can't simplify this. I just got to figure out what's going on. And so I would get 1 over 1 plus e to the negative infinity. So we got to decide, what's this thing doing? Well, when we have a negative exponent, we can write it as the reciprocal. And e to the infinity is a number raised to infinity. We get infinity, right? So this term right here is going to 0. So what are we left with?
1. 1 over 1.
1 over 1 would be 1. Okay, but let's look at the same function going to negative infinity. Now I already rewrote it with the reciprocal here. But now I've got e to the negative infinity, so we got to do the reciprocal again, right? So if I bring that up, it'd be e to the positive infinity, which is infinity. So we have 1 over infinity, which would be 0. Limit as x goes to infinity of sine x. What is the end behavior of sine? What's it doing?
Oscillating.
There is not a single y value that we can give as an answer for this, because it keeps changing, going between 0, 1, 0, -1, and back. Right? Remember, a limit is a finite y value. There isn't one. As I look way off to the right of the graph at positive infinity or at negative infinity. Okay, the same would be true of cosine, right? And what about tangent? All periodic functions just keep repeating with different values. So if I just ask you for the limit as x goes to infinity or negative infinity of a trig function by itself, the answer is going to be does not exist, because they keep repeating a pattern that is not approaching a single y value. Okay, what about limit as x approaches negative infinity of x cubed?
Just be negative infinity.
It'll be negative infinity. right? When we cube a negative, we get a negative. Infinity cubed is still infinity. It's a behavior. I'm approaching a number that I can't reach. All right, limit as x approaches infinity of this polynomial divided by this other polynomial. Okay, that's one of our rules for horizontal asymptotes from college algebra. If the degree of the numerator and denominator match, the answer is the coefficients. Okay, what about natural log of x? What is the end behavior? Well, for that one, I kind of got to know what the graph looks like. And you could graph it on your graphing calculator, because I don't think you have all the parent graphs memorized. But natural log does that. And while it's not growing real quick as I go off to infinity, it is continuing to grow. So it is going to infinity at some progression, if I could draw the graph going forever to the right. Natural log is the same thing as saying e to what power equals infinity. Well, e to the infinity equals infinity, right? So we get infinity for that one. What if I asked you what's it doing as I go to negative infinity? Now I just drew the graph. Can I go to negative infinity? Can I talk about what's happening at negative infinity for this graph? No, it doesn't exist over there. It's not in the domain. This next one, a little bit tricky. Because what I want to do is I want to say, oh, well, this 1 is insignificant. And it is. And then if I take the square root of x squared, we just get x, right? And x over x would be 1.
Something tells me that's wrong.
It's wrong. We're still going to ignore the 1. But what happens when I square the negative?
Becomes positive.
It becomes positive. So now I have negative infinity over the square root of positive infinity squared. Now I can simplify that. Take the square root of the square, it goes away. We've got negative infinity over positive infinity would be negative 1, not positive 1. So we've been building up to, and there will be a point where we do several lessons on what does the graph of a function look like, and one of the things we need to know is what are the vertical and horizontal asymptotes. So we now know that the vertical asymptotes occur when the denominator equals 0 and they're not removable. And the horizontal, we have to look at the limit as x approaches infinity or negative infinity. So let's start with that. My horizontal asymptotes will occur at positive and negative infinity. So now I rewrote this. I changed the order so that I can see the term with the highest degree, right? Because when we're talking about limits at infinity, we only care about the highest degree. So this looks like the limit as x goes to infinity of -1. And what do we get?
-1.
-1. All right, what about the limit as x goes to negative infinity? Because we got to check. They might not match on the left and the right. Well, we're still going to get -1, right? So for this one, we would say I've got a horizontal asymptote at y equals -1. And that would be occurring to the right and the left of my graph. For vertical asymptotes, we're worried about when the denominator equals 0. And can we remove them, right? Because if they're removable, they're just holes. Now, my numerator, not factorable because of the plus there. Otherwise, it would be a difference of squares. So there's nothing I can factor out of my numerator, so nothing I do with my denominator is going to cancel with the numerator. So we just want to look at when does -x⁴ plus x squared equals 0. Well, if I'm going to factor this, I really need to pull out the greatest common factor. And I'm going to pull out the negative with it so that I can factor what's going to be left over. So if I pull out a -x², I get x² minus 1. Well, that's a difference of squares. So I have three different factors here. I have the x², x plus 1, x minus 1. I'm going to have vertical asymptotes at each of those because none of them simplify with the numerator. So we'll get vertical asymptotes at x equals 0 from the first term. Don't forget about the greatest common factor that you pull out. X equals -1 and x equals 1.